Good morning everyone. Welcome to the 17th lecture of VLSI Interconnects course. Today we will be starting with the third module of this course, which deals about additional effects in interconnects. Previously in module 1 we have seen the RC interconnect modeling, and in module 2 we have seen the RLC interconnect modeling. So in both these modules we had about 8 lectures in each of these modules, and we were mainly dealing with the delay and overshoots present in the RLC interconnect. So in the last lecture we saw the simulation of RLC interconnect. In this lecture we will be starting module 3. So in module 3 we will be covering these following effects. So we will be studying what is a skin effect, how to model that. We will be looking at the power dissipation due to interconnects, thermal modeling of that is the modeling of heat dissipated in the interconnects, and the electromigration issues. In this lecture we will be starting with our discussion on the origin of skin effect. We will make some arguments on why the skin effect should arise, and we will also derive the current profile of an AC conductor in a conducting half space. So with that, let us start with the today's content. So again, when I start, I want to repeat that the accuracy of any model is limited by the phenomena that is captured or incorporated in that model. In the previous modules, we were looking at the RLC interconnect module and also the RC module model, and there we said that if I have an interconnect of a certain cross section, I can get the resistance for that segment simply as rho into L, which would be L is the length of my interconnect divided by W into H, where your H was the thickness of your metal of the interconnect and W was the width. So we had assumed in this model that my entire cross section is available for the for carrying current in this interconnect. But again, this model does not incorporate all of the physics that goes on, and that is what we will be discussing in this lecture and the subsequent 2 lectures. So all of you by this time, whether you are from an electrical background or an electronics background, you must have encountered the term of skin effect. Skin effect basically is the tendency of the high frequency currents and also fields to be confined near the surface of the conductor. So if you have a conductor and if the current is a high frequency current, then the current would tend to be concentrated near the surface of the conductor, and the concentration would be less or diminishing as you go deep inside the conductor. So why does this arise? We will look into that. So let us recap the case of DC. In DC, what we have is your frequency is equal to 0. So you have a 0 frequency signal. Suppose this is the interconnect. I have drawn it like this here. When I say a voltage this is applied, what I would assume that the entire cross section here is applied the same voltage here, right? So on this section the voltage is the same. So we have a simple equation: V is equal to I into RL. RL is the resistance of this interconnect, and then that is given by RL is equal to rho L by A. A is the cross sectional area. I can write this I as V by RL. I can substitute this value of RL here. So when I do that, what I get is I is equal to V by rho L into A. I can rewrite this as I by A is equal to sigma V by L. Here sigma is equal to 1 by rho, right? Sigma is the conductivity. So the current per unit area is my current density J. So this is my current density, and E is my electric field. So this is my electric field. In general, this relationship is a tensor equation, so you can also write it like this. But for a single case, I mean the direction does not matter, a single filament. So I can write J is equal to sigma E. So what happens is that a DC current, if the conductivity is uniform, throughout the cross section of the interconnect, then this current flows uniformly throughout. So whatever is the electric field applied at that point, the current would be flowing throughout the cross section of my interconnect. However, as we stated at the beginning, that the skin effect basically tells us that the currents and fields are confined more towards the surface. So let us try to first understand that in the case of an AC, why should the currents and fields be confined towards the surface? And so if the current is confined toward the surface, and since current is linked to the field, your field strength, or the electric field strength E, should also be lower towards the center. So why that would be there? So to understand it, let us try to form a complete picture of uh, the phenomena of how the current is carried here in the conductor. So if we take a DC case, let's again take a DC case. My electric field is going into the plane. So this is the symbol which I use to indicate into the plane. So my electric field into the plane, I'm looking at the cross section. So this is my electric field going into the plane. Of this paper. Right now, if my electric field is going into this plane, it will also introduce a current which will also be going into the plane. So there will be a current throughout. So yeah, this my current J, and J would be also be going into the plane. So this would be J is equal to sigma E, right? So here V is J is equal to sigma. Let me try to follow a color convention. So this is my E is my applied electric field. Now since there is a current which is flowing into this there would also be a magnetic field induced. Why? Because what you have is uh, your curl of H equal to K. Then there is another term here plus epsilon, but for DC case that goes 0. So for this DC case I am writing it like this. So there is this would be a magnetic field which would be induced here. How do we get the direction of that magnetic field? If the thumb points the direction of current, so yeah, so if my current points to in the direction of current which is going into the plane, and if I take my right hand, the thumb of my right hand, then the fingers would be giving me the direction of my magnetic field, because there is this curl in here, right? So in this case, the magnetic field lines would be induced, which will be clockwise when I am looking into the plane of the paper and current is going into the plane of the paper. Because if I point my thumb inside, pointing inside the plane of the paper, the fingers of my right hand would be curling in a clockwise direction. So this would be my induced, this would be my induced edge. Now the point to note here is that I can also write this in the form of a integral equation. So in that case, this would be dl is equal to whatever is the total area, so j into a total enclosed current, so this would be I j into d. Now the point to note here is that as my uh, as I traverse from this point towards the surface, my length, I mean the circumference of this integral scales linearly with the radius. However, the area scales as a square with the radius. So effectively, as I am going away from my away from the center of this conductor, I am enclosing more and more currents, and therefore my magnetic field intensity is expected to be more towards the edge as compared to the center. So that is indicated by the increasing size of these arrows in here. So this is so far so good, no issues with this. There is an electric field applied, it's a constant DC electric field applied, a current is flowing, because of the flowing current a magnetic field is induced. So no issues so far. But now we take the case of a AC signal. Your omega is not equal to 0. In that case, what we have is the following. So yeah, let me erase this part and make some arguments of what will happen now. What we have seen is that so we agree that there is again a electric field which is going into the plane of the paper, and then there is a current which is also going into the plane of the paper. Your current J is related to the electric field as per this equation, right? And as per this equation, and because of this J, there is a magnetic field which is H, or say curl of H equal to J. Curl, this magnetic field is going in this direction. But now we have another equation which we cannot ignore in the case of AC. What we also have is the curl of electric field, and that is given by minus mu del H by del T. Now in the case of AC field, this is a function of time, a harmonic function. So this is harmonically varying with e to the power j omega t. Similarly, this is also varying with e to the power j omega t, and therefore this h is also varying with e to the power j omega t. Right, so let me, since this is now a function of time, the derivative with respect to time will not be 0, and if I am considering a harmonic case, if I am considering a harmonic case, then then my induced electric field would be having uh, minus j omega mu h. So now h is going in this side, in this direction. Now if I want to look at the direction of electric field that would be induced, how do I do that? I take my right hand, the thumb of my right hand indicates the direction of h, so my h is in this direction. If I now, so the fingers of this my right hand would be giving me the direction of electric field. However, there is a minus sign in here, right? So there is a minus sign in here. So if I look at that, what I would get is that the direction of my electric field will be opposite to the direction of the fingers of my right hand if my thumb points the direction of my magnetic field. So what I have is this, my thumb is pointing in this direction, my electric field in that case would be circulating something like this. This would be the case, and it would be coming like this, right? For this is for this direction. If I take it for the current this direction, my thumb will be pointing in this downward direction. My fingers would then be curling in this direction, and since my there's a minus sign here, so I would be getting induced electric field in this direction. And similarly, an argument can be made that for the case of all the points here, there would be an electric field pointing like this in the center. So if I look at it, the induced EMF is actually opposite to the direction of the applied field. So if I look at it, my electric field is going like this, which is coming out of the plane of the paper. So my net field would be E applied and E induced. E applied is into the plane of the paper, and my E induced is out of the plane of the paper. And the fact that so if you solve for these equations, we can find that here there would be a, in this region there would be an induced EMF. The magnitude of this would be diminishing as you go away, and therefore the net field at the center would be less than the net applied electric field at the surface. And then this would also translate to the current density, and that is why what you would have is that the current density, so the current density at the surface is at the surface is more than the density at the center. So we have made a qualitative argument of why this skin effect would arise, but let us now go ahead and do a more rigorous derivation. So for the derivation, we again let's start simple. So let us consider a very simple case, a simplistic case of a half space of conductor. What it means is that I have my planes. So this is my x-axis, this is my z-axis. I have a half plane. So for all the region where z is greater than 0, my I have a conductor of conductivity sigma. So my conductivity is sigma. right? I am also assuming a simple current, so I am assuming that my current is going in the x direction only, because I have applied the electric field only in the x direction. So my J is Jx x hat, right? We also assume that the since this conductor is I can infinite half space, so it extends infinitely along y axis, and your del by del y is 0. So this is also important, and we will require this in our derivation. So your del by del y is equal to 0. Now let us start with the derivation. So what we have stated is that my J is equal to Jxx. This is related to the applied electric field, so obviously J is equal to sigma E, and my E can be written in terms of J as per this equation. We also assume a good conductor. So as I said, like in the previous argument, there would be an additional term of epsilon. We had ignored it there. Why we ignored it? Because we are assuming a good conductor. So what it means is that my conduction current, my conduction current is much greater than my displacement current. What it means is that basically my sigma is large, so my sigma is much greater than omega epsilon. So what I can do is that I can ignore this term. Ignore. So my h is simply my curl of h is simply given by J. So this is the assumption that I am making, that my conductor is large. So because my J is also equal to sigma E, so if my conductor is large, then this would be negligible. So I can neglect that part, right? Then I have this equation. So this is the, let me number it, the fifth equation. So what do I have? I have a equation relating J and E. So I have an equation relating J and E. I have an equation relating E and H, and equation relating H and J. What I want a differential equation in a single, in one for one quantity, and that I can solve. Since I'm interested in like the profile of current in this conductor half space, I will eliminate my H, E and H from these three equations and write the differential equation in terms of J only. So eliminating E is simple. I just replace E by J by sigma. So that's what I have done here. So I have this as equation number 6. Right, so okay, let me not mark highlight every equation. Right, so I have this equation, I can rewrite it, and I can write this J as curl of J. So now I have two equations. One equation is curl of H is equal to J, and then I have equation curl of J, which is equal to minus J omega mu sigma H. Right, now since we are here, let us take the curl in the Cartesian coordinate. What we had assumed that my J is simply Jx x hat. So if I want to take the curl, I will write it like this. Also note that we had assumed that there is no variation along the y direction, so this goes to 0. Now if I solve this, basically if I want to get the component along x, I will get 0. You can check the how to get the determinant. If I am looking in the y direction, then I will have this is 0 minus and there is a minus sign also here, so I will finally get del j by del jx by del z. So this would be my curl. What is the number? This would be numbered as 8. Right. So basically from here, from 8 and 7, I can write my I can write equation 7 in the form as this, and I am numbering it as 9. Now let us come to equation number 4. So for equation 4, let us take the curl of h, and that curl of h is equal to jx x hat, right? So what I will so again this goes to 0, and since there is only the x hat here, so I have to just compare the coefficient of the x hat. So if I do that, I will get this as my equation. So this is equation number 10. Right. So note that from here also you can see that there is only the y component of your magnetic field, right? Because curl of j is only in the y direction. So if this is equal to this, so only y component of my magnetic field is non-zero, and that is also seen here, that only the y component is present and only the jx term is here. Now in from equation 9 and 10, from equation 9 and 10 we eliminate hy. So from equation 9 and 10 we eliminate hy, and finally we get a nice expression, nice differential equation in this form. Here we I mean from here we know how to solve it. So I mean I can replace this partial derivative with respect as a d by dz. Why? Because there is no variation along the y direction, and I'm also assuming a time harmonic case, right? So that derivative with respect to time has already been eliminated. So I can define this as a new variable. I'm naming it as gamma square, where I can write gamma as root over j omega mu sigma, and I can write the solution jx in this form. Let me continue with the numbers. So this is 11, this is 12, or say this is 12, and this is 13. Right. So what we have is this, where gamma is a root of imaginary number. How to get that root? I can write j omega mu sigma as this is my magnitude, and this phase term I can write as e to the power j pi by 2, right? And now if I take the square root of this, I am taking the square root of the magnitude and dividing the argument or the phase by a factor of 2. So I have sigma is equal to, given by this thing. I can expand this e to the power j pi by 4 in terms of cos pi by 4 plus j sin pi by 4. So pi by cos and sin pi by 4 is equal to 1 by root 2. So I can write gamma like this. I can club this root from root 2 with this constant or this term. So finally I get my gamma as 14 and then this is 14. Right, I can again define a new variable which I am calling as this delta, and I can call this equation as 15. So now if I substitute this delta in here, so delta is a constant, a positive number, right, and then gamma is 1 plus j divided by delta. So if I substitute it here, I can write my gx as a e to the power minus j minus 1 plus j z by delta. Note that the dimensions of delta is is in meters, right? So it's in the units of space. So what you have is z divided by delta. This is sort of a constant which has dimensions of the same as z. So I have this. What I can see is that there is a real term here. So this e to the power minus z by delta. So this would be attenuating. Right? So this would be the attenuating term, and this term would be uh, this term would be amplifying as z. So as z increases, your this term would diverge, resulting in the total current. So the current would also diverge. Current tends to infinity as z tends to infinity. This is not the case that we are considering, because this won't satisfy the condition of finite current. So therefore this constant b can be eliminated to be 0. So b is 0, and we are what we have is this remaining part as jx as a function of z, a e to the power minus 1 plus j z by delta. Here delta you can see we define as the skin depth, and we will discuss that in more detail. So what we have is that at the surface your z is equal to 0, and from that I can, so if I substitute z is equal to 0, what I have is jx of 0 is equal to a. So I can replace this. A basically means the surface current density, so I can replace my my constant a by the surface current density j0. Finally what we have is the current governed by this equation. So we can see that there is a phase term here as well. This does not contribute to the diminishing magnitude, but there is e to the power minus z by delta, and we can see that this current density exponentially decays below the surface of the conductor. So this was the surface of my conductor, right? This is x, this is z. So the current density here is j0, and then below the surface it goes on diminishing. So delta is the distance at which your skin depth or sorry the current density decays to decays to 1 by e times. So this delta we will discuss more in detail in the next lecture. So this is what gives me the skin depth and skin effect of for my conductor. So I would sincerely ask you to do this derivation on your own. In the next lecture, we will continue with this discussion, and we will see how this skin effect leads to what is the effective resistance of your interconnect. And at high frequencies, the resistance itself becomes a function of frequency. And so we'll look at the expressions for that case in the next lecture. So with that, I will stop here. We'll meet in the next lecture. Good day.